So we can continue this morning session, which is somehow no longer morning because noon is approaching. And the next speaker is Professor José Gálvez Rodríguez from Spain, from Almeria. The title of his talk is Riemann Integration on a Space with Fractal Structure. So please start.
Okay, thank you very much, and thank you to all of you for giving me the chance to introduce my work here in this conference. And well, the main goal of this talk is going to be how to get another theory, which is really similar to Riemann's theory, the classical one everybody knows, but using fractal structures. So the structure I'm going to follow in the presentation is the one you can see here. First of all, we are going to recall some concepts and results of the classical Riemann theory. Also, I will talk about fractal structures, and then in the rest of points, we will see the new theory that we have recently published in as a research work. So, well, according to fractal structures, they were introduced recently in the literature in order to characterize non-Archimedean quasimetrization, although they can be used in different topics, for example, metrization, topological and fractal dimensions, and similar sets, filling curves, compactification. And well, I have to say that one of the last applications that have arisen from fractal structures have to do with the construction of a probability measure on a space. Indeed, this talk is going to be related in some sense with this topic, because maybe in the future we will be able to get the density function of a distribution function by using the integration theory we are going to show here. But a fractal structure, which will be denoted by like this, defined on a set, is a countable family of coverings that we will denote like this, such that each covering is going to be a strong refinement of the previous one for each natural. Recall that a covering is said to be a strong refinement of another one if each element on the second one is a refinement of the other one, which means also that each element of one of them is contained in some element on the previous. And also each element that we consider in one covering can be decomposed as the union of elements in the next one. We will refer to that covering as the level n of the fractal structure. And here you can see one image in which we have give a representation of the natural fractal structure on the unit interval. You can see here that in the first level of the fractal structure, we divide it into intervals with the same length. Then we repeat that procedure in the next level by dividing it also into 4 parts, and we can continue recursively in order to get the rest of the levels. Now, this is what we have to know about fractal structure in this talk, and now we are going to recall some results on the Riemann integration theory. Recall that a compact interval in the n-dimensional Euclidean space is the product of intervals, like you can see here, and the volume of this interval is going to be defined as this product you have here. Also, we can give a partition of this compact interval, which is going to be a set of partitions of each of the intervals we can see in J. It equivalently is going to be a sequence such that the points can be written like this, and also can be seen as the sequence of compact intervals. This you can see. Also, we have to know that the partition norm is defined as the maximum of the difference between the elements in the sequence, and the partition is going to be called a refinement of another partition if the sequences on the first one are subsequences of the sequences in the other one. Also, when we have a bounded function of an interval and a partition of this interval, The lower and upper Darboux sum of the function in that partition are defined from these quantities you can see below, and the lower and the upper Darboux sum are this one you can see here. Note that we are considering each of the set of the partition we have taken, and also the product between the quantities. You can see here the infimum and the supremum of the images of the points, and the product with respect to the volume of the set of the partition we're considering each time we sum. Well, so given a bounded function of on an interval, on a compact interval, and a partition of this interval, the lower and the upper Riemann intervals of the function over that interval are defined like you can see here. And in case that both values are the same, we say that the number is going to be the Riemann interval of the function over the compact interval, and will be denoted by this. Well, a theorem, which is classical also, is that a function is going to be Riemann integrable if and only if, for each positive epsilon, there exists a partition such that the difference between both sums is going to be less than epsilon. Also, in the classical Riemann theory for intervals, we have that a selection for a partition is basically a collection of points that we take one in each element of the partition. And also we define the Riemann sum for a function relative to the partition and a selection as the sum you can see here, which is really similar to the one we have introduced before, but now the points are taking one in each interval of the partition. Hence, we have the Riemann's theorem, which says that a function is going to be Riemann integrable if and only if there exists a number, which is going to be the value of the interval then, with the following property. For each epsilon, there exists a positive delta, such that the difference between the sum relative to the partition and the selection, with the difference with the limit is going to be less than epsilon for each partition, such that its norm is less than delta, and for each selection we have considered. And in this case, we say that if the function is Riemann integrable, that the limit is the interval of the function. Well, so now we have the basic concepts and results of the Riemann integration theory. Next step is start developing a theory, but using fractal structure. The idea is to consider a fractal structure instead of a partition, because a fractal structure is going to be a partition. And also, instead of using the volume of the set, we are going to use a measure. So first of all, we are going to consider a measure space and a fractal structure on that space. And we are going to say that the fractal structure is going to be Moody's joint if the following conditions hold. We are going to suppose that each level of the fractal structure has a countable number of elements. Also, that the measure of the intersection of two sets is going to be 0 in case they are different. And also that the measure of each set is going to be finite. Well, so it seems natural to define now the lower and the upper Darboux sum by taking into account the Riemann integration theory. So given a measure space, a fractal structure which is going to be Moody's joint, and a function which is going to be bounded, for each element in a certain level, we set these two quantities. You can see that they are the same that in the classical Riemann theory, using the infimum and the supremum. So that the lower and the upper Darboux sum with respect to the measure and for each level the fractal structure are going to be given by this expression. We take the infimum, the supremum, and also we consider a measure which, as I said before, is going to be like the volume in the classical case. Well, so now we have the lower and the upper sum, Darboux sum, next step is defining the Riemann intervals of the function with respect to the measure and the fractal structure. And they are going to be defined as you can see here. The upper Riemann interval is going to be defined through the infimum of the upper Darboux sum, and the lower Riemann interval is going to be defined from the supremum of the lower Darboux sum, which also meets the limits you can see here. And well, so if we have a measure space and with disjoint fractal structure and a bounded function, a function is going to be said to be Riemann integrable with respect to the measure and the fractal structure if both upper and lower Riemann integral are finite and they meet.
I'm sorry.
If,
I'm sorry at this moment. Could you recall mid-disjoint? What does it mean, mid-disjoint?
yeah, mid-disjoint means that each level is a countable family in the fractal structure. Each level is going to be countable. Also, the measure of the intersection of two different elements is going to be 0, and also that the measure of each element in the fractal structure is going to be finite.
Thank you, sorry.
Yeah. So now if we come back to the definition to upper Riemann interval and lower Riemann interval, so it makes sense to define a Riemann integrable function when they both meet, when the lower and the upper Riemann interval meet, and also we will denote like this the set of Riemann integrable functions with respect to the measure and the fractal structure. So now we can give a first result. We can have a measure space, a mode-disjoint fractal structure, and also a bounded function defined on that space. And the following statements are equivalent. For example, claiming that a function is Riemann integrable with respect to the measure and the fractal structure is going to be equivalent to claim that for each positive epsilon, there exists a natural such that the difference between the upper Darboux sum and the lower one is less than or equal to epsilon. And well, we can also claim that statement by using the definition of the convergence of a sequence in terms of a certain natural. Well, now recall that we have talked about a selection of points in the Riemann classical theory. So now we can consider a fractal structure, which is countable for each natural, and a selection for a level is going to be a collection of points such that each point belongs to just one element in the chosen level of the fractal structure. Also, we can define the given a measure space and with disjoint fractal structure and a bounded function, given a natural, and also a selection for that level, the Riemann sum for f relative to the level, the selection, and the measure is going to be denoted by this, and it's going to be the sum you can see here. It is also analogous to the one we have defined in the classical Riemann theory. And well, if we have this concept, it also makes sense to talk about a Riemann theory, but in the context of fractal structures. So, given a measure space, a disjoint fractal structure, and a bounded function, and also a point, a real point, the following statements are equivalent. So, being Riemann integrable with respect to the measure and the fractal structure, and such that the interval is C, is equivalent to all those points you can see here. In terms of convergence, we can characterize the fact that a function is Riemann integrable with respect to the measure and fractal structure by using the sum relative to the selection we have considered in each case. But now we should ask something ourselves. And it's really important, this proposition, because when we have a measure space and a fractal structure, well, two fractal structures, which are Moody's join, it can be proved that given a bounded function, if both functions are Riemann integrable with respect to the measure and the corresponding fractal structure, it can be proved that both integrals are the same. So, if we have a look at this proposition, we can claim the next definition. It does make sense perfectly to talk about this concept. Given a measure space, a bounded function, the function is going to be more Riemann integrable if there exists a Moody's joint fractal structure such that the function is Riemann integrable with respect to the measure and the fractal structure. And in this case, the integral is going to be defined like this. So it is really important because in case we find a fractal structure such that the function is Riemann integrable with respect to the measure and that fractal structure, the value of the integral is going to be the same for each other fractal structure such that the function is Riemann integrable. And then if we take into account that result, we can prove that given a measure space and a bounded function, then the function is going to be Riemann integrable and our integral is going to be the same as the classical Lebesgue measure. So this is also an important thing, is that the Lebesgue measure, which is also classic, can be calculated by using the integral we have introduced here in terms of limits and sums which are related to the levels of the fractal structure. But the idea is to find the fractal structure, because in case we find one which is suitable, we can calculate integrals each time we need.
I'm
And
sorry,
as a consequence,
5 minutes, I'm sorry, 5
okay,
minutes.
perfect. And as a consequence of this fact, we can recall that each continuous function is also measurable. So when we have a topological space and a finite measure on the Born sigma algebra of this space and the bounded function, then the function is going to be Riemann integrable on X. So once now we have related our new integral to the Lebesgue measure, but in the next result, in this proposition, we are going to relate it to the classical Riemann integral. Note that if we consider a compact integral and a bounded function, and we consider the natural fractal structure that we have seen in the previous example, then the function is going to be Riemann integrable in the classic sense if and only if the function is Riemann integrable on the space with respect to the Lebesgue measure and the natural fractal structure. And in this case, if the function is Riemann integrable, both integrals are the same. And as a consequence, by taking into account the previous results we have seen, if we have a compact integral and f is a Riemann integrable function, then this function is going to be Riemann integrable with respect to the Lebesgue measure. And we don't have to talk about the fractal structure because we know that the natural one is going to be suitable in the proof. And finally, I'm going to show you an example in which we can calculate an integral, an improper integral, which is really typical, but using the theory we have introduced in this talk. We are going to consider this space, the Lebesgue measure, and the function defined by this exponential one. Now consider that the fractal structure is the natural fractal structure, which consists on the subdivision of intervals of x by taking half and then the half of a half. And we can now calculate the Darboux sum. The lower Darboux sum, it's really easy. The operations we can do to conclude that is going to be this series, and the upper one is going to be this one. So if we do the difference, we get this quantity, which is convergent to 0. So using the previous results, we can claim that the function is Riemann integrable with respect to the Lebesgue measure and the fractal structure. And also, we can calculate that integral by taking limit of each of the Darboux sum. And the result is 1, which is the one you can get by using traditional operations. So it follows that the function is Riemann integrable with respect to the Lebesgue measure. The result is 1, and this interval meets the improper classic Riemann integral. Finally, here you are the main reference of the recent paper we have published to have a look at all the proofs and other results we have got in this context. So thank you very much for your attention. It's been a pleasure for me to taking part in this conference.
Thank you very much.